All right, this is the periodic chart on page C6. Let's try to generalize our understanding of this. Now look, chemistry can be really complicated. Obviously, there are people who take these big, long, difficult courses called chemistry classes, and it's not easy. But on the other hand, it's actually much simpler than you might have thought. Watch this, because it actually starts to reveal the entire magic of chemistry. We know that the elements in column 1 all have one electron in their outer orbit. That's why they're in column 1. Atoms with less than 4 electrons in their outer orbit do what? They give them away. So every single element in column 1 is going to give away that one lone electron in its outer orbit. Last class meeting, we drew a picture of hydrogen, lithium, and sodium, and all three of them have one electron in their outer orbit. Now, column 7, the halogen family, fluorine, chlorine, bromine, and iodine, they're in column 7, VII, which means each of them have 7 electrons in their outer orbit. They're only 1 electron short from having that outer orbit be full with 8. So can you see then that any element in column 1 will combine with any element in column 7? They're perfect matches. So for example, we can have sodium chloride, that's salt, right? Sodium chloride. We also mentioned last class meeting sodium iodide, right here. We can have sodium, in fact, fluoride, sodium chloride, sodium bromide, sodium iodide. We can have potassium fluoride, potassium chloride, potassium bromide, potassium iodide. You start to get the idea? We can have lithium fluoride, lithium chloride, lithium bromide, lithium iodide. Because these elements all give away 1 electron to elements here that all want 1 electron. So we start to understand how this works. Yeah?
What about the other column, 7G? Will they also combine with those?
It gets a little bit more complicated. We're trying to keep it simple. If I could present everything there was to know in a year-long chemistry course in 2 class sessions, that would be extraordinary. All right, so there must be more. In column 2, of which calcium is in column 2, all of these elements in column 2 have 2 electrons in their outer orbit. And any atom with less than 4 gives away those outer electrons. So each of these is going to give away its 2 outer electrons. Now, we saw that sulfur today is in column 6. All of these elements in column 6, oxygen, sulfur, selenium, beryllium, all have 6 electrons in their outer orbit. The outer orbit holds usually up to 8. They're each short of 2 in filling that outer orbit. So we just saw how calcium could combine with sulfur, forming calcium sulfide. But calcium could have also combined with oxygen, which also needs 2 electrons, because it's got 6, forming calcium oxide, right? So we can see how all of these can combine. We could have magnesium can combine with oxygen, forming magnesium oxide. Magnesium could combine with sulfur, forming magnesium sulfide. So any element in column 2 can combine with any element in column 6. Do you see how this starts to work? Now, it can get a little bit more interesting than that. You'd say, well, how? All right, consider this. Calcium, we said, is going to give away its 2 outer electrons. Right? It's got 2 electrons that it's going to give away. We just said that. We had given you the example of calcium giving its 2 electrons to the same atom, to sulfur, that wanted to. But would this work? Could calcium give one of its electrons to a chlorine? Remember, a chlorine only needs 1 more electron. But could it give the other electron to another chlorine? That would also add up, wouldn't it? Calcium's still giving away its 2 outer electrons, but instead of giving it to a sulfur atom that takes both of those 2, it gives one of its electrons to chlorine and the other to another chlorine, and this forms what's called calcium chloride, or CaCl2. And that'll add up too. So I think that you're starting to see how, basically, this is the magic of chemistry. It explains why certain elements combine with other elements. Just another thought on this. Clearly, though, we would never see, let's say, 2 elements in the same column combining with each other. You cannot have a sodium combined with a potassium. They both want to give away electrons. All right? So that's just not going to work. So the way this works is it's got to add up correctly. All right, and when you take advanced chemistry classes, they actually call this balancing the reaction in terms of understanding this movement of transfer of electrons between the different types of atoms that are in a chemical reaction. All right, so we're starting to understand the magic of chemistry, and we have to have some knowledge of chemistry in order to understand the chemicals that are found in living things. And on page C3, so just to remind you of what we had covered on C3, so we had introduced the concept on page C3 of compounds. A compound is something made up of two or more kinds of elements in a specific proportion. So water is hydrogen, two hydrogens and an oxygen. Salt is sodium and chlorine. Baking soda is sodium and hydrogen and carbon and three oxygens, or sodium bicarbonate. Now, we had learned that the smallest amount of an element you can have is a single atom of that element. We talked about that on the first lecture. So if we had a chunk of gold, the smallest amount of gold we can have is a single gold atom, because there are gold atoms, and there are uranium atoms, and there are carbon atoms. The smallest amount of a compound we can have is a single molecule, a single molecule. So the smallest amount of salt we can have is a single molecule of salt. The smallest amount of water we can have is a single molecule of water. Now, what we were starting to learn that what holds atoms together is called a chemical bond. We call these chemical bonds that hold atoms together. And there are two major categories of chemical bonds. There are what are called ionic chemical bonds and covalent chemical bonds. I just played earlier today that catchy little rhythm of asking what type of relationship are you, or bond, talking about ionic bonds and covalent bonds. So those are the two basic types. An ionic bond is an electrical attraction between two oppositely charged ions. So that's what we see holding a sodium ion and a chloride ion together. What's holding them together is an electrical attraction between two opposites, something that's positive and something that's negative. So this usually we see ionic bonds between a metal and a nonmetal, between a giver and a taker, between opposites. Now there's also something called a covalent bond. Co means to share, to share. You know, a co-pilot shares the responsibilities of flying a plane with a pilot. Co means to share. Valent means electron. So literally, a covalent bond is a sharing of electrons. This is different than an atom that gives away an electron to another atom that takes an electron. Because what's also possible is a sharing of electrons. Now this sharing of electrons usually occurs between two of the same kind of atoms. Two of the same kind of atoms. Now, the number of electrons they share can vary. They could be each sharing one of their electrons with the other one. That's called a single covalent bond. They could each be sharing two electrons with the other. That's called a double covalent bond. Or they could be sharing three electrons with the other. That's called a triple covalent bond. So we're going to give you an example of this right now. So we're going to look at page C11. On page C11, so in the upper diagram, we've already covered it. This was showing an ionic bond. The attraction, the electrical attraction, you say what page? C11. This was showing the electrical attraction between a giver and a taker, between a metal and a nonmetal, between two opposites. In the lower half of the page, it shows covalent bonds. What are covalent bonds? The sharing of electrons between two of the same kind of atoms. Now you've got actual pictures here, and if you're thinking, you know, that's fine, Professor Fink, that's nice that you have pictures, but they would be a lot better in color. Guess what? In your textbook, they're in color. All right, chapter 2. We're all the way to chapter 2 in this course. All right, so here it's showing the sharing of electrons between two chlorine atoms, two chlorines. Here it's showing the sharing of two electrons each between two oxygen atoms, and at the bottom it's showing the sharing of three electrons each between two nitrogen atoms. But you've got these pictures, you can study them on your own and look at the pictures in color in chapter 2 of your textbook. I want to draw these same things using the electron dot diagram. So I've done that right here on the side. You could do this on a separate piece of paper, you could do it on the side just as I have. So now I'm just using that electron dot diagram to show the exact same thing that's shown in the picture at the right. So what are we showing? We show two chlorines. I made one of them blue and one of them red. They don't really come in different colors. Now, each chlorine has 7 electrons in its outer orbit. We know that. It's shown right at the top of the page where it shows sodium combining with a chlorine. Chlorine has 7 electrons in its outer orbit. Now remember, if chlorine has 7 electrons in its outer orbit, what does it desperately desire? 1 more electron to fill that outer orbit with 8. So, imagine, this almost sounds like the setup for a joke. Imagine we've got 2 chlorines standing on a corner. One chlorine turns to the other chlorine and says, I really need an electron. All right, the other says, me too. All right, and they say, you know, sodiums, they always give away electrons. You see a sodium? No, I don't see any sodium. You see any sodium? No, I don't see any sodium either. One chlorine looks at the other, and they said, let's share. So what they do is they each share one of their electrons with the other one. Now you'd say, what does that mean? That means that 50% of the time, this blue, and they're not really blue or red, but this blue electron of this chlorine is going to come over to the red one, and it will have the 8 that it wants. Everybody follow that? And 50% of the time, the red electron will go over to the blue one, the blue chlorine, and it will have the 8 it wants. Now you might argue, but wait a second, Professor Fink. When that blue electron is going over to the red chlorine, that means it won't have 7, it'll actually only have 6 at that moment. This is called sharing. Let me explain how sharing works in the example of having 2 children share toys with each other, right? Sharing doesn't mean you get what you want all the time or even half the time. It means you give so that you can receive. That's called sharing. Now, sharing in relationships is very, very important, all right? And it's rare to have these perfect 50-50 sharing. When you have it, it creates a very strong relationship where each party shares equally with the other party. They each give equally and they receive equally. But they are giving. You have to give before you receive. So that's called sharing. Now, there is a common way of representing this sharing, each one sharing one of its electrons with the other. We draw a line between the 2 CLs, and that line represents that they're each sharing 1 electron with the other. We could also write this as just Cl2, 2 chlorines together. Incidentally, this is actually written right here. It may be written small, but that's actually what it shows right below the actual pictures of the chlorines, showing them sharing their electrons with each other. It says Cl2 or Cl-Cl. All right, so it all means the same thing. So I've given you an example right now of 2 chlorines, each sharing 1 electron with the other. Let's give you a second example. The second example is 2 oxygen atoms. 2 oxygen atoms. All right, now is oxygen an important thing to talk about for a biology class?
Yeah.
Well, yes it is, because you're breathing oxygen at this moment, so I guess so. So oxygen atoms are each going to share 2 electrons. Let's remind you of oxygen. Now, we've already seen pictures of oxygen, originally on page C7. On page C7, you've got a picture of an oxygen atom in the 2nd row on page C7. And you'll notice that oxygen, it says oxygen, has 6 electrons in its outer orbit. And each oxygen wants 2 more electrons. You'd also know this on the periodic chart, because oxygen is in column 6, the same as sulfur. All right? Now, I'm not asking you to memorize atomic numbers or atomic weights. I'm not asking you to memorize which column on the periodic chart an element is in. I'm asking you to understand the concepts. And there's some of you who are following the concepts as I speak about them, and some of you I've already lost in the dust. Well, most of what I'm saying today, you have no idea what the hell I'm talking about. Now, it's not too late to catch up, but as I said last class meeting, in a couple of weeks it will be. And that means you'll be out of the class, and the class won't be as full. All right? I'm not saying I want that to happen. In fact, I'm telling you I don't want it to happen. But you have to do your part to make it so it doesn't happen. All right, so let's use a dot diagram to show this. All right? So this time, our focus is right here. And what I've drawn is two oxygen atoms. Let's even enlarge it. All right, there it is. Two oxygen atoms. Ignore the chlorine on the top. All right, here's a blue oxygen and a red oxygen. They're not really blue and red. Each oxygen atom has 6 electrons in its outer orbit. After all, it's in column 6. So this blue oxygen has 6 dots around it, representing the 6 outer electrons. And this red oxygen has 6 dots. Now, what would each oxygen like to have to be happy? 2. It wants a total of 8. Each one needs 2 more electrons. Right? So just like sulfur that we talked about today. Now, again, this is going to sound like the setup for a joke. 2 oxygen atoms are standing on the corner. One turns to the other and says, boy, I really could use 2 more electrons. The other says, so could I. I really would like 2 more electrons as well. So my outer orbit is filled to capacity. So one oxygen says, do you see any calcium? They always give away 2 electrons. You see a calcium? No, I don't see any calcium. Do you see any calcium? No, I don't see any calcium. So one oxygen turns to the other turns to this one, and they say, let's share. They're each going to share not 1 electron with each other, but 2 electrons with each other. Now again, just like in the case of the chlorine above, if the 2 blue electrons spend 50% of their time around the red oxygen, it will have the 8 that it wants. And 50% of the time, 2 of the red electrons will go go over to the blue oxygen. Does everybody follow? So they're each sharing not 1, because that wouldn't be enough. They each need 2. So again, sharing means, it doesn't mean you get what you want all the time. It means you give half the time and you receive half the time. That's called equal sharing. All right? So this could also be written this way. We said that we draw 2 O's, or oxygen, for oxygen. Each line represents a sharing of 1 electron. We drew 2 lines this time because they're each sharing not 1 electron with each other, but 2 electrons with each other. This is also written as O2. Everybody has heard of O2. That's oxygen. An oxygen molecule is made up of 2 oxygen atoms joined together. Each of the 2 are sharing 2 electrons with each other. That's really what oxygen is. Now, I want to give you a third example. The third example is shown at the bottom here of this page C11, and it shows the sharing of electrons between 2 nitrogen atoms. Now, our first thought is, well, who cares about nitrogen? I mean, I never even heard of it. So let me ask the following question, and I wrote it right here. What is air made of? What's air made of? Now, if you ask most people would say air is oxygen. Most people would be wrong. The actual chemical composition of air is about 20% of the molecules in air are oxygen. Only 20%, 1 out of every 5 molecules that you inhale. Almost 80%, 79.8, almost 80% of the molecules that are in the air, that make up normal air, are nitrogen gas, N2. Now, it's not a full 80%, it's 79.8. So in other words, if oxygen makes up 20%, and nitrogen makes up 79.8, that's a total of 99.8% of the molecules in air, right? So the remaining difference, everything else in the air, hydrogen, neon, air pollutants, everything else accounts for less than 0.2% in normal air. You'd say, what if it's really a smoggy, really polluted day? It's still less than 0.2%. All right? So obviously the major thing we inhale with each breath is nitrogen. Now living things don't use nitrogen, whatever nitrogen they inhale, they then just exhale it right back out. But it is the major thing that's going into their lungs. Oxygen is actually used. So let's use a dot diagram to show what happens with nitrogens. Now, each nitrogen has 5 electrons in its outer orbit. Again, you could look up nitrogen on the periodic chart. Frankly, there was a picture of nitrogen we looked at last class meeting. It's on page C7. Right on page C7 was a picture of nitrogen on the right-hand side of the first row on page C7. Right? It's on page C7 on the top right. So it had a picture, and it showed that each nitrogen had 5 electrons in its outer orbit. Or you could just look on the periodic chart, because on the periodic chart, nitrogen is in column 5. It tells us that it has 5 electrons in its outer orbit. Right? So, what we've done is, just like I did with those other cases, we've got 2 nitrogen atoms, one's red, one's blue. They each have 5 dots, or 5 electrons in their outer orbit. 1, 2, 3, 4, 5. Same thing with the blue one. 1, 2, 3, 4, 5. Now, any atom with more than 4, is it a giver or a taker if it's got more than 4? It's a taker. It's more than halfway to 8. It's more than halfway. So each nitrogen wants how many more to make that outer orbit full? It needs 3 more to make the outer orbit full. 8. It's got 5. So, again, sounds like the setup for a joke. 2 nitrogens are standing on the corner, right? And one turns to the other and says, boy, I could really use 3 more electrons. The other says, so could I. And again, they're looking for atoms that give away electrons. Those are called metals. But what they can do is they can each share 3 electrons with the other. Because that means if 50% of the time, the blue nitrogen will have 8 electrons by getting 3 from the red nitrogen, and 50% of the time, the red nitrogen will get 3 blue electrons from the blue nitrogen, and they're each sharing 3 of their electrons with the other one. This could also be represented this way. Here, we've drawn 2 nitrogens, 2 ends, each one, and we drew 3 lines between them. Each line represents sharing of 1 electron. So they're not sharing 1 electron, they're each sharing 3 electrons with the other. That's called a triple covalent bond. Or we could just write it N2. A nitrogen molecule is made up of 2 nitrogen atoms, each sharing 3 electrons with the other. Incidentally, all this is shown right here in your picture. Shown right in your picture. It's written small, but obviously as I magnify it, you can see that's exactly what was printed right there. N2 or N with 3 lines between the other end. It's also shown in your textbook in chapter 2, which I strongly recommend you read and look at the pictures. All right, we've been talking about back on page C3. We've been talking about covalent chemical bonds. And that takes us to water on page C3. You'd say, what page are we? C3. Now, water is really important in terms of living things. Water makes up 60% of your body weight. So however much you weigh, 60% of your weight is water in all normal people. And in terms of at the cellular level, 80% of a cell, of what's inside of a cell, is water by weight. Water is so important in making up living things that we cannot imagine life existing anywhere in the universe if there's no water there. So when we knew that there was no water on the moon, even before they landed a man on the moon, we knew there was no water, and obviously after they landed, they didn't see any water either. So nobody was expecting or has ever thought that there would be life on the moon. Because if there's no water, whatever else may be lacking, we just can't imagine life as we know it existing without water. What interests biologists or exobiologists, biologists who look for life and study life elsewhere in the universe, is that Mars, the planet Mars, appears to have some water on it. Now that doesn't mean that it will end up having life, because it takes more than just water to have life. Mars is further away from the sun than the planet Earth, and it's really, really cold there. But at least the possibility exists that there could be life on Mars, whether there ends up being life or not. But the possibility, the potential exists because there is water there. So that's what excites people who study the planet of Mars, why they want to study it further to see if there is any primordial or early forms of life, simple life that might be there. Maybe not, maybe yes. All right, so water is really important. Now, why is water so important? It has to do with the structure of water. Because of the structure of water, it creates some unique properties that make it different from any other molecule. Now, let me zero in on water. If we wrote that hydrogen and oxygen atoms that make up a water molecule are held together by something called polar covalent bonds, which involves an unequal sharing of electrons. So I need to explain that. So and again, I drew this here. I know it's easy for me to zoom in on it, and you might say, yeah, but there's not a lot of space. You can draw it anywhere you want. And remember, anything I talk about is in your book. I'm not just making this up. All right, so here, well, you know water is H2O. All right, so what I did is I drew an oxygen atom, and I drew two hydrogen atoms. There they are, that's a water molecule. But we've started to understand in more detail what holds molecules, atoms together in a molecule. And so we are reminded that each oxygen atom has 6 electrons in its outer orbit. We've learned that, said it several times today. We just looked at the structure of O2, 2 oxygens joined together. Now, if each oxygen has 6 electrons, and it wants a total of 8, then each oxygen wants 2 more electrons. Now, hydrogen has 1 electron. It's the simplest of all atoms. It's got 1 proton and 1 electron. Now, hydrogen is an interesting atom. It's an interesting type of element. Here's why. And again, if it helps you to visualize this, you can look back on page C7 to help you visualize this. On page C7, we had a picture of hydrogen on the top left. All right, so here's hydrogen. This is page C7 on the top left. And so it's got 1 proton and 1 negative charged electron. Now, on the one hand, we've been talking about an atom that has less than 4 electrons in its outer orbit gives them away, or if it has more than 4, it takes. But we've been assuming that it's an orbit that holds a total of 8. So if it's got less than 4, it's less than halfway to 8. But hydrogen has 1 electron in its outer orbit. That first orbit only holds 2. Hydrogen is halfway there. It only holds 2. So does it give it away or does it take? Sometimes it gives and sometimes it takes. It's halfway there. It's not a matter of being less than halfway or more than halfway. It is exactly halfway. The first orbit only holds 2. And so hydrogen sometimes gives, but it actually likes to try to share. It actually likes to share. So that's what's going on in a water molecule. So hydrogen wants to share its electron with the oxygen. Now think about this. If oxygen needs 2 more, it could get 1 electron from the hydrogen and another electron from this second hydrogen so that it would have the total of 8 that it wants. Does everybody follow? And then oxygen is happy. And then the hydrogen needs 2, right? It needs 1 more. It's got 1, and it would like to grab that blue one, so it would have 2 electrons, which fills that first orbit. So these 2 hydrogens could share their 1 lone electron with the oxygen atom, and oxygen would share 2 of its electrons with the hydrogen. Now all this sounds great. It sounds like it's a perfect match. Only one thing. In the earlier examples that I gave you of sharing, it was always sharing between 2 of the same kind of atoms. We give you the examples of sharing between 2 chlorines, sharing between 2 oxygens, sharing between two nitrogens. And when two of the same kind of atoms share, they share equally. But oxygen is a much bigger atom than a little tiny small hydrogen. And oxygen will share, but it doesn't share equally. It takes more than it gives. Now, I know that as I say it, you're thinking, I don't know, I'm mixed up. He's not very clear. Let me make it in terms of a human relationship so you can relate to it. All right? We have talked about two types of relationships so far. We've talked about an ionic relationship. Let's see if I have a paper that summarizes this. Yeah. All right. So we're going to talk about three types of relationships. And we can think, even though we're dealing with chemistry, most of us are probably more interested in human relationships than chemistry relationships. And we're going to see that it's not a lot of difference. We've talked about an ionic bond. Again, I want to remind you of that catchy little video that we have that you can watch. An ionic bond is an attraction between a giver and a taker. That's not a very strong bond, a very strong relationship. If the only thing you've got going for the two of you is an electrical attraction of two people who are very opposite to one another, you may be exciting for a while, but it's probably not going to last. Because there's not a lot that you share in common. In fact, you don't share at all. One gives and the other takes. So after a while, the one person who's giving all the time is going to say, I've had it, because I only give in this relationship, and the other party only takes. That's what's going on with salt, and it's not held together by a really strong relationship. We're going to see that salt tends to break apart. Now, we've also mentioned a covalent bond. The word covalent, number 3, literally means to share electrons. Co means to share, valent means electron. We saw that two oxygen atoms can equally share two of their electrons with another oxygen. And when we say equal, we mean equal, 50-50. That's a very strong bond, a very strong relationship. So oxygen doesn't tend to break apart very readily. But now we've just introduced you to a new type of relationship. I listed number 2. It's called a polar covalent bond. Putting the word polar there means unequal. It's an unequal covalent bond. That's what we see in water. So you'd say, so how do you explain that? This is actually what most human relationships are. Most couples are sharing. They just don't share 50-50. In most couples, one of the parties tends to give more and the other tends to take more. Think that's right?
Yep.
All right? If you're in a relationship, you know, of course, the other, it's always the other party that's not giving enough. But anyhow, so you can ask both people in the relationship, and they both say, "I'm the one who's giving." But what they do agree is that's not equal. All right. So most human relationships, it's really rare to find that perfect 50-50 balance of a giving and taking. Usually, in most real relationships, one person does tend to give more than the other does. So in fact, the relationship that exists in the water molecule, this unequal sharing, is actually similar to most human relationships. This perfect balance here between two similar atoms that have everything in common, that's really a very strong relationship. So now that you've got that down, so now let's come back to the water molecule. So this is page C3 again, on C3. So what we've said is that oxygen is going to share its electrons with hydrogen, but not equally. It's going to take more than it's going to give. We might call this relationship between oxygen and hydrogen is not 50-50, but more like 60-40, or maybe even 70-30. You follow that?
Yep.
Oxygen is taking it more than it's giving because it's bigger than the hydrogens. So if the hydrogens are giving more than taking, that means these negative charged electrons are spending more time with the oxygen, so the hydrogens tend to be positively polarized. Or think of it this way. It is a positive virtue to be a giver, and hydrogens are giving more than they're receiving, more than they're taking. So that gives them a positive polarity. Oxygen is taking more than it's giving of those negative charged electrons, so it's got a negative polarity. Now, here's where it really gets fun. You're going to think all entirely differently about chemistry in just a moment. So let me just summarize so far that this bond between the hydrogen and oxygen is called a polar covalent bond. What does polar mean? An unequal. Covalent means sharing of electrons. All right? So that's what's holding oxygen and hydrogen together. Now, here I drew just another example of just another water molecule. Right here. All right, so here's the water molecule. I just used lines to represent that they're sharing, but I did indicate that the oxygen is negative and the hydrogens are positive. Okay, here's where it gets really fun. What if you're in a relationship and you're not really getting everything out of that relationship you'd like? You know what people start to do? Yeah, start to look elsewhere. Start to be more attracted to other things going on around you. So imagine you're this hydrogen atom right here who's giving more than you're getting. So here's another water molecule. Here's another water molecule right here. So here's another O with two H's. So imagine this is a hydrogen that is wedded to this oxygen in this water molecule. It's attached to this oxygen, but it is electrically attracted to this other oxygen. Now, the real reason for this attraction is that the hydrogen has a positive polarity, and remember, every oxygen's got a negative polarity. So this is really just an attraction between opposite attraction, opposite electrical charge, or polarity. But to make it so that you can remember it, the hydrogen is essentially wedded or bonded to this oxygen of this water molecule, but because it's not getting everything it'd like out of the relationship, it's attracted to the oxygen of another water molecule. Now, when a hydrogen atom is attached to one atom but attracted to another, we call this weak attraction. The weak attraction, W-E-A-K. The weak attraction that hydrogen has for another oxygen that it's not really bonded to, we call that a hydrogen bond, an H bond. Now you might say, did you write any of this stuff? Well, first I want to remind you it's all in the book. I'm trying to get you to read the book. But yes, I did. Right here, we've already said that the hydrogen and oxygen atoms are held together by polar covalent bonds involving an unequal sharing of electrons. And then right below that we wrote, there is an electrical attraction between the water molecules due to hydrogen bonds. So there is this attraction between the water molecules. So that I drew here 3 water molecules. You'd say, where? Here's a water molecule, here's a water molecule, here's a water molecule. Does everybody see that? And in all 3 of those cases, you'll see that even though this hydrogen's attached to this oxygen and this water molecule, but it's attracted to that one. Here's another hydrogen. It's attached to this oxygen of this second water molecule, but it's attracted to a third. In other words, in a glass of water, this is what's going on. Everybody's got affairs with everybody else. Think about that when you drink that glass of water. All of these water molecules, and each water molecule is made up of an oxygen and 2 hydrogens that are attached to the oxygen, but all of these water molecules have this electrical attraction to other water molecules because they're not getting everything they'd like out of the relationship. This is like a French movie. If you've ever seen a French movies are always the same subject. You know, they're always the same subject. It's always ménage à trois relationships. There's always a couple that's married, and they each have some affair going on the side. Has anybody ever seen a French movie? That's what they're always about. So this is like that glass of water is like one French movie that's where everybody's got affairs going on the side. It is this phenomenon that there is this electrical attraction between the water molecules that creates the unique properties of water. And that's what we wrote, letter C, right here. Water is a unique compound with unique properties. There is really almost no other substance that has the unique properties of water for the reasons that I've explained. And let's mention some of the unique properties of water that no other liquid or any other substance has. Number one, water has a very high surface tension. So our first thought is, what's that? So, if you spill water on the floor, if you spill water on a tabletop, have you noticed that the water molecules seem to all coalesce or bead together? Right? Has anybody ever noticed? You spill the water and it actually starts to draw together. They call that beading up or coalescing. Does everybody notice that?
Yeah.
That's because of that electrical attraction between the water molecules. They all want to kind of fuse together. If you spill gasoline on a table, or rubbing alcohol, or ammonia, it won't do that. Water does, because of the phenomenon we've described, what's going on. Another unique property of water, something that's even more important in terms of living things, number two, is that water resists temperature changes. In other words, when it's hot, water tends to absorb heat and make things cooler. But on the other hand, when it's cold, water tends to actually retain heat and make things warmer. Here's how you can relate to this. All right, when it's really hot, it's always cooler by a large body of water, a lake or an ocean, right? Now, this next one is also true, but you may not be as familiar with it. When it's really, really cold, it's actually going to be warmer by the large body of water. You know, let me be more precise. It hasn't been that cold lately. I know some of you are saying, yeah, it's freezing last night. It wasn't freezing, all right? But let me ask you this, and you'd have to know a little bit of, get out of, Culver City to know this. All right? When it's really when it's cold or a cold night, is it colder here or is it colder in the valley? In the valley, farther away from the water. As you get closer to the water, it's warmer. So a lot of people like to live by oceans or lakes because whenever you're by a body of water, it's more moderate in temperature. When it's hot, it's not as hot. When it's cold, it's not as cold. When you're farther away from a body of water, it's more extreme. In the valley, it's got even hotter summers than we do here, but it's also got colder winters than we do here. They get frost on the lawns when it's really cold in the valley. So water moderates the temperature. So why is that important? If the major chemical that makes up a living thing, including us, is water, that tends to keep the temperature of our body more constant because water tends to basically moderate the temperature. It resists temperature changes, is the way I wrote it. Now, a third really weird characteristic of water is that we wrote that solid water, which we call ice, is actually lighter, less dense than liquid water. You'd say, what do you mean? So, if you have a glass of water and you drop some ice cubes in it, which is just frozen water, don't the ice cubes float? Water is the only substance like that. Every other substance, when you go from a liquid to a solid form, the solid form is heavier. So in any other case, when you cool something down and turn it into solid form, it becomes heavier and it sinks. Water is the only substance that when you cool it down, it becomes lighter. When you turn it into a solid water or ice floats. Think about the importance of that to fish that live in a lake. If as water froze, if it started to freeze and turn to ice, it would start to sink, crushing all the fish in the lake. But in fact, as water freezes, it rises. And the fish are still swimming under that frozen lake and below the frozen water. Another unique property of water, number 4, is that more substances will dissolve in water than any other liquid. So it's commonly called the universal solvent. If you spilled something right, on the floor, on a table, on a couch, the first thing you usually try to remove whatever you spilled is water. Before you resort to anything else, you usually try, well, water, just remove it. Because more things will dissolve in water than anything else. We've got all kinds of chemicals in our body and in any other living thing, and they dissolve in water more than any other liquid. And another characteristic of water, water disassociates. You'd say, what's that? It breaks apart molecules held together by ionic chemical bonds. You'd say, I don't get that. So I drew some extraordinary pictures here at the bottom. Okay, they're not so extraordinary. And I just drew them in the bottom. There's enough space. Yeah, let me give a bigger version. But whether you draw it at the bottom or any other page. So these are 3 beakers. 3 beakers. All right, so in the beaker, and all 3 beakers are filled with water. All 3 beakers are filled with water. I'll walk through each of these, so you might say, give me a second to write it down. Okay, we'll give you time because I'm going to explain them. So in this first beaker, it's filled with water, and we're just going to drop, let me just enlarge just this first beaker so we can stay focused on that for the moment. So we're going to drop some salt in it. Now salt, sodium chloride, what's holding sodium and chlorine together? An ionic bond. We've just told that an electrical attraction between 2 opposites. And we've already told you that's not the strongest relationship. So these are all held together by ionic bonds. So in fact, when we drop salt into water, this attraction is cooled down by the water. You know, you have this hot attraction between a giver and a taker. Water spills water. It's like cold water over the relationship. The salt breaks apart into sodium ions and chloride ions. Remember, these are ions because sodium gave away its electron, chlorine took, so they have an electrical polarity. So when you drop salt into water, you don't have salt molecules floating in water. You have sodium ions and chloride ions. Now, of course, if the water evaporates, they'll come back together again. But water, we said, breaks apart any molecules that are held together by these electrical attractions called ionic chemical bonds. All right, everybody okay on that? Let's try a second example, beaker number 2. This time, we're going to take a beaker filled with water and drop hydrogen chloride in the water. Now, hydrogen chloride is just, instead of sodium chloride, it's hydrogen chloride. It's also more commonly known as hydrochloric acid. What's holding the hydrogen and chlorine together is essentially an electrical attraction. Let's drop it into water, and now it separates into hydrogen ions and chloride ions. Can you see again that water has caused a molecule that's held together by an ionic bond or an electrical attraction to break apart, to disassociate? Everybody okay on that? Now, we're going to come back to this third picture, but just before we do, let's look on page C4. We'll come back to that. On page C4, what is an acid? Now, we've all heard the term acid, but what is an acid? This is just page C4, the back side. All right, so an acid is any substance that yields, that forms hydrogen ions when it breaks apart, when it disassociates. So any chemical that releases hydrogen ions when it breaks apart is called an acid. I don't know what you thought an acid was, but that's the definition of an acid. So, going back to our picture, that's why hydrogen chloride is more commonly called hydrochloric acid, because when you put it in water, it forms free hydrogen ions. It's an acid. All right, now let's look at this third example. In this third example, we've got a beaker of water, and we're going to drop sodium hydroxide into the water. So our first thought is, what's that? Well, it's NaOH. Na is sodium. OH is hydroxide. It makes sense because it's got a hydrogen, hydra, and an oxygen, oxide, hydroxide. Now, interestingly, what's holding sodium hydroxide together, we know that sodium is always a giver. It gave to chlorine. It's a metal. So sodium is a giver, that's a positive thing, right? It's positively charged. OH together is called hydroxide, and it always takes an electron. So that combination of oxygen and hydrogen together always grabs onto an electron. That's a negative thing to be a taker. So what's holding sodium hydroxide together is an electrical attraction between a giver and a taker. So when we drop it into water, water cools off that relationship, and it breaks apart into sodium ions and OH, or hydroxide ions. You'd say, oh, that's nice, so what? Well, and I'll come back to this page one more time yet, but look on C4 again. On page C4, what's our definition of a base? Our definition of a base is a substance that yields, that forms, that releases hydroxide ions when it dissociates. So anything that releases hydroxide ions when it breaks apart is called something that's basic. That's the opposite of something that's an acid. So going back to that picture one last time. So in fact, sodium hydroxide, also known as caustic soda, not soda like soda pop, but soda because it's got sodium, and it's very corrosive, very caustic. It's also known as lye, and I'd like you to know that, lye, L-Y-E. It's the active ingredient in Drano and liquid plumber. So what's in Drano or liquid plumber is not a strong acid, but just the opposite, a very strong base. Now, very strong acids or very strong bases are equally very corrosive. So now we know the definition of an acid. An acid is something that gives off hydrogen ions. A base is something that gives off hydroxide ions. Let me ask you a question. Is salt an acid or a base? It's neither. It's neither. I didn't say it had to be one or the other. It doesn't give off hydrogen or hydroxide ions. Salt water or salt is not an acid or a base. Nobody ever said it was. All right? But this is an acid and this is a base. So on page C4, so now that we've explained what an acid or a base are on C4, what is something that's neutral, that's neither an acid nor a base? It means that it has the same number of hydrogen ions as hydroxide ions. So salt water was neutral because it didn't have hydrogen, didn't have hydroxide, it had zero hydrogen, zero hydroxide, so it's neutral. But even if a solution did have one hydrogen, but it was balanced by one hydroxide, they would balance each other and it would be considered neutral. Now we have something called a pH scale. The pH scale runs from 0 to 14. Obviously, what's the halfway point between 0 and 14? 7. All right, so any solution that has a pH of what we say 7 is said to be neutral. So what's an example of something with a pH of 7 that's neutral? Pure water, pure water. Now remember, water is H2O. But another way that I could draw water is instead of writing H2O, I could draw water HOH, couldn't I? HOH, that's two hydrogens and an oxygen. So in fact, if a water molecule were to break apart, and some do, after all, remember they're not really happy in their relationships, sometimes they divorce. So anyhow, if a water molecule were to break apart, the way it breaks apart is it breaks apart into one hydrogen ion and one hydroxide ion. But it still remains neutral because they're equal in number. Now, any solution that has more hydrogen ions than hydroxide ions is said to be acidic if it's got more hydrogen ions. Any solution that's got more hydroxide ions than hydrogen is said to be basic, or alkaline, or caustic. All three of these words mean the same thing. So whether we say basic, or alkaline, or caustic, it means they have more hydroxide ions than hydrogen ions. Now, the more hydrogen ions that a solution has, the lower its pH. So a solution that has a pH of, say, 5 would have more hydrogen than hydroxide. If it's got a pH of 1, it's got even more hydrogen ions. If it's got a pH of 0, it's essentially all hydrogen ions. In the opposite direction, any solution with more hydroxide ions than hydrogen ions would be said to be basic. So a solution with a pH of 10 would have more hydroxides than hydrogen. If it's a pH of 13, it's got even more hydroxide ions. And if it's a pH of 14, it's essentially all hydroxide ions. So that's how this pH scale goes. Let's take a look at page C12. C12. So on page C12, again, some of you might say, Professor Fink, is this in the book? You know, I'm going to let you look at chapter 2 to find out. All right. So on page C12, it just shows this pH scale. In this case, they drew it vertically instead of me the way I drew it on page C4 horizontally. You'd say, I don't get it. Well, look, here it shows the pH, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Does everybody see it's just vertical? So here at pH 7, it says pH 7 is neutral. It has an equal number of hydrogen ions as hydroxyl ions. What's an example of something with a pH of 7? Pure water. Because as we've said, pure water is really H and OH. Now, let's give you some examples then of some things that are acidic, in increasing acidity. You'll notice that saliva and milk, actually they're still about neutral, but you'll notice that sour milk, milk that has gone sour, actually is now slightly acidic with a pH that's lower than 7. Urine tends to be on the acidic side. Remember, the lower the number, the more acidic. You'll notice that coffee and tea are even more acidic than sour milk. Beer is even more acidic with a pH of 4. We're going to be learning that what makes beer acidic is that beer contains something called carbonic acid in it. We're going to be learning that. Now, vinegar is even more acidic. It's got actually something called acetic acid in it. It's got a pH of 3. And notice that all cola drinks, in fact, all carbonated drinks are acidic. And what does carbonated mean? It means they actually contain carbonic acid. That's why they're called carbonated drinks. Well, more to say about that. You'll notice that orange juice and pineapples and tomatoes are acidic, right? And if you're into referring to foods as yin or yang foods, these are your yang foods or acidic foods. There are foods that are high in acid. There are foods that are low in acid. All right? Lemon juice, which has citric acid in it, is pH 2. Lime juice is even more acidic than lemon juice with a pH of 1. And stomach acid, the juice in your stomach, has a pH of 1. That's because there is an acid in your stomach called HCl hydrochloric acid, which we had just mentioned on page C3. Now, if we talk about battery acid, it's approaching pH 0. You don't want to spill battery acid on yourself because it'll dissolve right through your skin. All right, one last thing before we call it a day, and then we continue this on Monday. In terms of an exam date, I'm going to give you a tentative date momentarily. So here, next time we'll go over those that are more alkaline, and we're going to be finishing up chemistry.